We're now considering section 5 of the first chapter of our textbook, Introduction to Python, with a discussion on some of the important functions available in the Numpy library. As I mentioned before, Numpy is an important library that you need to be able to have access to for a lot of the subsequent lectures that we're going to do with applications in scientific computing. So we'll start off with some very simple functions that are still very useful for initialization in particular. As you see on the screen, the first function, zeros, ones, and a range are functions provided in Numpy. Zeros is a particular way of initializing an array to be all 0 elements. The name of the function is called 0, and you'll notice the parameter list is indicated. Actually, the very first parameter of zeros as well as ones is actually a tuple. If you recall, tuples are delineated by parentheses. And this tuple has two components to it, dim1 and dim2. You can think of that as the number of rows, dimension 1, and the number of columns, dimension 2. And then the actual second parameter is just a specification of the data type, integer, float, whatever. So, and most of the time you're using zeros and ones for floating point or integer arrays. So ones is very similar to zeros. It's just a way of initializing all the components of the array. In this case, you're basically thinking of a two-dimensional array here to be all ones, again, according to the specified data type. There's also a very useful function called aRange. We've seen range before as a way of generating a list of items that can be used for an iterator variable, say as part of a for loop. aRange does not return a list, it returns an array. We'll see examples of array in just a second. And the way it works is you have a starting element in the array, and up to a boundary element is the second parameter. So the second one is a boundary, which we'll see an illustration of that again. And then the third parameter is the increment. So that 2, when I say from 2, 2 acts more like a boundary, up to but not including that particular value. So if we use the from import structure for statement for getting the particular functions that we need out of Numpy, we could import array and say the float function, which is a way of being able to specify floating point values for an array. After doing that, we can actually call the array function, which is indicated here in this next line. And you'll notice that the input to an array, to the array function, are lists. So in this particular case, you have two lists. Each list is delineated by the square brackets, and you've got two of them. Comma separates two of them. And the interpreter is able to figure out exactly what kind of dimensionality you have here, because you have two lists and each list has two components. So it basically treats each one of those like a row of a 2 by 2 matrix. So when you go to print A, you actually get what is indicated in blue right here. This is the output, print A, if you pass those two lists to the array function. Again, the first one is basically considered like the first row of a matrix, and the second one is the second row, and everything should be conformable. You have for 2 rows and 2 columns. Below is another way of calling array. You don't always have to pass literal floating point values like we did the first call. You could give it a list that have integers in them and then have it convert them all to floats and storage. So turns out this print B will actually have the same output as indicated on the screen. So both of those prints generate that two-dimensional array with 2, -1 on the first row and -1, 3 the second. Also notice there's no commas here. It's very important. Notice that arrays will not have commas. It'll be more like a matrix. When you were taking linear algebra class, for example, you don't ever put commas when you're describing it. So there won't be any commas associated with arrays from Numpy. Let's look at some more examples. Here's an example of, again, from Numpy import these three particular functions, a range, zeros, and ones. Again, a good idea to tell the someone using your code exactly what functions you're importing. Here we're calling a range to return an array, not a list, but an array, and it says start with the value of 2. Increment by 2, that's the third parameter, up to but not including 10. Remember, that's very similar to the way we think of slicing. Students get this confused. Sometimes some people would say, oh, isn't that a 5-element array? No, it's a 4-element array. It starts at 2, it goes up to, but does not include 10. So therefore, the only elements in this array are 2, 4, 6, and 8. Again, 10 is a boundary. So keep that in mind. And on the output here, when you ask the interpreter to print A, you get an array. Again, notice there are no commas. That is how you know it is an array. Here's an illustration of the simple call to ones function, giving the tuple 3, 3, which tells the interpreter, construct this as 3 rows and 3 columns, and the data type is float. All ones does is put ones in all the array elements entries, and because we have the shape specified by the tuple, you get a 3 by 3 matrix. Again, the tuple is telling it the shape. The rows is the first element of the tuple, and the columns is the second. So let's look at how you can change and modify array elements. We'll again import from Numpy. Let's just say for purposes of needing all the available functions, we'll put import star, and then we call the zeros function to create a 3 by 3 matrix of zeros. So there are 3 rows and 3 columns, and the interpreter is told to store them as floats. So all the elements are stored as the zeros initially are stored as floating point values. Now, the fact that you use lists to build an array, you can index an array the way you would components of a list, in the sense that this first particular call here, a bracket 0, really refers to the first row of the two-dimensional, of the 3 by 3 array. So it's a 3 by 3 matrix, and that's referring to the first row. A bracket 0 would be the first row. A bracket 1 would be the second row. A bracket 2 would be the third row. Input to that, again, to the array function was a list, and if you're going to modify a particular row of the 3 by 3 matrix, you actually specify it as a list. So this is a way of taking the list 2.0, 1.1, 1.5, and replacing it by the and substituting, in for the first row of the 3 by 3 matrix A, which of course was all zeros. So we're going to print the final A here at the bottom, but you can see initially we have loaded that particular list into that first row. And again, when you print an array, there will be no commas, even though we build the array with lists. The second change is just to replace the element in position 1, 1. Now keep in mind 0 indexing. That's not the first row and first column. That's the second row and the second column. And hence you notice that 0 that would have been that position is not there now, and it's been replaced by this 5.2. So finally, what we do is a slice here. Now let's pay attention to slicing. The first particular index here does specify the row. Second, the 2 would define the third row with 0 indexing. So we're looking at the third row, but in terms of the column positions, we're using 0:2 notation for a slice. That means we would start in column position 0, but go up to but not include column position 2. So remember how that the value, that integer that comes to the right of the colon in a slice, means up to but not including. Again, those of you familiar with MATLAB, or if you think about C, sometimes this can get confusing. So that means 0, starting with 0 but up to, but not including 2. That is really just 2 elements there of that column. It's the first 2 elements of that column. The first 2 columns in that particular row. So it only manipulates the 8 and the negative 3.3, which it's going to get from the list. It's going to take those elements from the list and overwrite the zeros that would have gone in those positions. Okay, so notice this. This is exactly why you will have 8, negative 3.3, and then 0 for the last row, because you've only changed the first 2 columns of that last row. If you wanted to change the whole row, again, you could have used a bracket 2, or you could have said a bracket 2 comma 0 colon 3 if you wanted to, because that would have gotten that last 0 to be replaced. But then, of course, you would be using a list with 3 items. So everything should be sort of conformable. There's only 2 elements over here in the list, and that's only corresponding to 2 indices that are going to come out of that slice. Looking at some other examples, we're going to show you that sometimes functions from one library may have the same name as a function from another library, but clearly they're not the same in terms of what they operate on and what their outputs may be. So here you'll notice that we're doing an example where from Numpy we're importing an array, which we've already seen. It's going to help us build like matrix structures. But also we're importing a function sqrt, which you would think of as the square root function. Important thing to realize is this is not the square root function from math. This is the square root function from Numpy. So what's the difference? This square root function applies to inputs, which are arrays, not just regular scalar values, just regular single numbers that we've seen before. So if you did not import this sqrt function and then apply it, as you see down here below, on an array, that would generate an error, because the interpreter would say, I have access to a square root function, the one from the math library, but it doesn't understand what an array is, because an array completely isn't a function that's provided by Numpy, not the Python core libraries that you get by default. So you have to pay attention to that. If you need certain operations to perform on arrays, make sure you find the ones that are available, probably from Numpy or some other library, but most likely from Numpy. So here's an example of, suppose we took a 4-element list, passed it to an array, so we would generate one-dimensional array A with the components 0, 4, 9, and 16, all as floats. Notice that you can do things like this. You could say, well, I'd like to divide every element of that array by the value 16. So nice thing about the interpreter, it can actually replicate that operation across all the elements. No need for a loop at all. It's wonderful. And so what happens here is 16 gets divided into every one of those elements, and hence in blue here you have the result. And of course those are all floating point values on the output, because the original array was built with floating point values. Similarly, you could do subtraction as indicated next here. Every element of the array is subtracted by 4. And then at the very bottom again is an example of square roots. This square root function was imported from Numpy. It will take precedence over the previous math one, and you can then take the square root of every element of the array. And the output, of course, is an array. Notice there are no commas. So again, don't get confused. The input to the array function is a list. But from then on, in terms of manipulating the array A, it would not have commas if you were to print. Now, linear algebra is made easy with the array. That's why Numpy is very important to have, and that's why we insisted that you make sure that you install it with your Python interpreter. So here's an example. For generality purposes, let's say we want to access all of Numpy, so we would do from Numpy import star, the wildcard. And then what I'm showing you here is how you could initialize a 3x3 matrix with particular values, not zeros or ones, and you'll notice arrays being passed a list of 3 lists. So notice very carefully, you lead with the bracket, and then you have a list with the 2 brackets, another list, comma separated, and then finally another list. There's 3 lists there. You have a list of 3 lists. Again, continuation is easily specified by the / operator there. And the interpreter is smart enough to realize that it was given 3 lists, and each list had 3 items in it. Therefore, it's basically creating a 3x3 matrix. And by coding it the way I've coding it, you can actually see the matrix very clearly. Okay? But the elements are comma separated because they're lists. Then I'm also creating a simple vector or one-dimensional array, calling it B, by passing the list 1, 4, 2, all in floating point. Now, here's an illustration of a very important function called dot. Dot stands for dot product. And in this particular example, if you were to pass, say, a single vector, for both operands, b, comma b, to dot, you're basically computing the dot product of that vector. What does that mean? If you remember from linear algebra, that's just b transpose b, which will translate into the sum of the squares of the elements of b. So that'd be 1 squared plus 4 squared plus 2 squared, and if you sum that up, you would get 21. So that would be the dot product, or b transpose b for all purposes. Now, you can also use the dot product function to do matrix vector product that you learned from linear algebra. In this case, you would be taking the matrix A and multiplying it times the vector B, a very standard operation in linear algebra. And if you may or may not remember, by definition, what that is taking dot products between every row of your matrix with that corresponding vector B. So for example, you would take the dot product of 4, -2, 1 on the first row, dot product with B, and get -2. Then you would take the second row of the matrix, -2, 4, -2, take the dot product with B and get 10. And then finally, you would take the dot product between the last row, the third row of this matrix A, and B, 1, 4, 2, and get the value -1. So that is the matrix vector product. So, but it's the same function dot each time. A couple other examples. Again, this is just repeating the 3x3 matrix and the vector B that we created before. There is another built-in function for Numpy has called multiply, and you've got to be very careful. This is not the same thing as the vector matrix vector product we did a minute ago. This is a little different. This is very, very useful for scaling the matrix if you're just, for example, trying to change the columns. So what happens here, if you look very carefully at this matrix A, look at the first column, 4, -2, 1. The multiply function will take the first element of this array B and multiply it times the first element of every element of the row, or the first element of every list used to build the array A. So essentially, the first column remains unchanged because the first value of B was 1. Then it moves over to this to the element in the second position, and it multiplies everything in the second column of the matrix by 4, and hence you will get -8, 16, and -8 there. And then finally, the last element of B, which is 2, gets multiplied by the third and final column of the array, or the third element of each list, and you would get this final element, the final column there, 2, -4, 6. So that is one way of achieving a scaling of the original matrix by a vector. Scaling each column of A by this corresponding element of B. There's some other nice functions if you wanted the diagonal of that matrix. If you just read down the diagonal there, you could see it very clearly. The diagonal there is 4, 4, 3, very simply. And you can get subdiagonals if you want, or superdiagonals, depending upon if you put 1 or minus 1 and so forth. That just means the next diagonal below the main diagonal is -2, 2. And the trace is just the sum of the diagonal elements, which would be 11. So there's lots of linear algebra functions that are provided in the Numpy library. And the last slide in this particular section, again, using our working example of the 3×3A matrix and the vector B, is that you can use the argmax or even argmin function in a very nice way, especially if you're trying to do some type of search or sort. Sometimes it's very nice to know the index of the largest element. And so, for example, here we're just trying to tell me the index in the vector B that corresponds to the largest element. Clearly the largest element of this is 4. What position or index is that in the array? It's the second position, which of course is indexed by 1 if you think about 0 indexing. Again, if you did argmin, the smallest element would be 1, and then the corresponding minimum element would be, the index for that element would be 0. And then finally here you could, the identity matrix can always be created. The identity function does not need a tuple because it's understood that it's square matrix, so the number of rows and columns is the same. It just needs to know the order. In this case it's 3, and what's generated is a 3×3 identity matrix made in this way. Last thing to remember is the difference between alias and copying. If you had a statement something like D equals A, where we've created this 3×3 matrix with the array function from Numpy, if you set D equal A, you're just getting an alias for A. In other words, whatever manipulations you do to that to D would be the same thing as doing it to A. That's just an alias pointing to the same memory. If you need a separate copy of an array stored in memory, you need to use the dot copy syntax. In other words, copy is a function that's built in for all the array structures, any array structure you create. So if you use a dot copy, you would be specifying that you're going to create new memory and load every single element of the array A into this new array C.